Good morning and welcome to MFC Group's FasTech Seminar series hosted by FH Sales. Thank you for joining us. Today we're spotlighting CAN versus 10-base T1S, when to make the Ethernet switch with Microchip. Our speaker for this seminar is Pete Ormsby, and Pete has been an FAE at Microchip for over 6 years, specializing in Ethernet, USB, and PCLE. He previously worked as an FAE with FPGAs and as an electrical design engineer in aerospace and medical electronics markets. Pete went to school at North Dakota State University and University of Iowa. Go Hawkeyes. Everyone is muted, so please type any questions that you might have throughout the presentation into the meeting chat. We'll monitor the questions and make sure that we answer them at the end. At the end of the presentation, I'll also unmute everyone so that you can ask questions if you would like to. And at the end, please hang around for a fun round of trivia, where the top 3 winners have the ability to win a prize. Disclaimer, if you are not allowed to accept prizes, you're still welcome to have fun, and you can just decline the prize at the end. And with that, Pete, I will turn it over to you.
Excellent, thank you. So just the reason why this screen is up as you see it right now is most of the material that I've got in this presentation I've derived from our master's class that we had last August. Every year Microchip has a master's conference in which we do a kind of university style training, and so this is actually a 2-hour class with an hour and a half lab all about T1S, and so this is kind of a subset of that. So I'm going to squish it down to about 30-40 minutes of slides, and then we'll go into that. But again, this is something that we do at Microchip every year. If you're interested in kind of seeing what's coming up, you can get to the masters off of the Microchip webpage. But this is the kind of stuff that we do there. And with that, and just so you understand, this presentation is really going to be talking about the new kid on the block, which is the 10-base T1S. CAN stuff, I'm assuming you understand that. I will draw some comparisons, really from a high level of why you'd want to use it, not so much at a technical level about signaling and that kind of thing in the CAN space. But with that, I will go ahead and start. By the way, if you have any questions and stuff, you can go ahead and type them in the chat, and then we will have the Q&A at the end. All right. So let's go here. All right. So really, this has been driven by the automotive market. CAN's got a big place in the automotive market, and this T1S is kind of Ethernet's version of that. You can see that a car has a lot of electronics in it today, and there's just a wide variety of the current cars today, of the communication standards that is used in it. There's a lot of different things that are used in the cars today. And not only that, an industrial market also is a very similar kind of place where you have a bunch of different Ethernet and Ethernet-like kinds of things, along with I2C and UARTs and SPIs and RS-485. There's just a lot of communication schemes. And what happens with that, you have a lot of issues with gateways, and you have a lot of, not issues necessarily, but a lot of effort is into taking one of these communication schemes and bridging it to the next one. What happens frequently, especially as security is becoming more and more important, now you have to really basically have these nodes not only translate the form of the packet, but you're ripping down whatever security that you're doing on one network and then building it back up on whatever security you're using on the next network. And so now you have all these places here where you are unencrypting and re-encrypting, or you are checksumming, and there's effort in that bridge between them. And the differences in the kinds of wiring you need and the kinds of connectors you need, and all of these kind of things just makes multiple networks make work. It's an issue. And so when you look at doing Ethernet across the scheme, the big hole in Ethernet is that it's really not very good for low speed kind of networks where you've got a common bus and across it's Ethernet traditionally at most layers is a point-to-point kind of network, and it just makes star kind of networks required. It's really hard to do any kind of kind of smaller sensor kind of networks. And so T1S is there to address that. Um, and therein, probably more than any other reason, when you talk about why you should be looking at T1S versus CAN, is that T1S physically looks like CAN. It can do a lot of the things CAN does, but it from a software standpoint, at the data frame level and above, it's just all Ethernet. So it is the attractiveness of that is there's none of this bridging. When you sit at your laptop and you go and you send an Ethernet packet off into the ether, um, it doesn't that application that you're doing, it doesn't know if you're on Wi-Fi or if you got a fiber connection on that. It doesn't know if you're going to be going on a microwave link or a satellite bounce or whatever with that data frame. It's Ethernet. It just goes Ethernet. And T1S is exactly like that. You don't have to have any special coding in your network to say, hey, this is going to be a special CAN-like kind of a bus. It's just Ethernet. Ethernet frame goes all the way down to the end. You have Ethernet addressing all the way down at the end. It just happens to be a multi-drop bus like CAN. So anyway, this is the attractiveness of the CAN. And I should also point out that the other thing that's new about this kind of Ethernet is that it's a single pair. T1S is a single pair with multi-drops on it, but even at the 100 megabit and the gigabit and even faster than gigabit levels, there's these new T1 versions of Ethernet that are just a single pair of wires. And obviously, the reason that you want to do that kind of thing in a car is that going from 4 wires to 2 wires is a weight savings, 75% drop in weight savings. And when your Ethernet harness in your car is the third heaviest component after the engine and the transmission, it really makes sense to get simple wires, get a standardized interface, and get everything looking the same from a software standpoint. It just makes life easier. So as we move into kind of the new next generation networks and stuff, all of these kinds of features that have been built in part of Ethernet for a very long time now go all the way down into your CAN-like networks without a huge amount of you're not inventing anything new. Ethernet has had security and such for a very long time. So all of this stuff just flows. So anyway, the automotive guys, they've got a lot of reasons to go look at this. And the industrial guys do as well when they're talking about the density of wiring that they have in their switching boxes inside the factories and such. And it is just less expensive to run 2-wire connecting as opposed to a Cat 5, Cat 6, or even Cat 7 kind of connection. So what is T1S? This is kind of what I'm going to get to describe it. I've been saying it's CAN-like. From a functional standpoint, it can do just about everything that CAN can do. And we'll go into kind of what it looks like. So it's a single twisted pair. It is a multi-drop bus. It is an IEEE standard. So it's if you've got a T1 connection, T1S network, people who make T1S nodes can plug into your network and it will work like Ethernet does. The spec for the T1S is that it's one of these interesting kind of specs they're doing now. It's a minimum maximum, meaning that you can specify the maximum number of nodes that you support on your T1S. But that number has to be at least 8. Doesn't mean that you have to have 8 nodes on. You can have 3 nodes, you can have 4 nodes. But the spec for your maximum number of nodes has to be at least 8. If you can only support 7 nodes, you're not compliant with the spec. But if you support 50 nodes, you're still good. That's compliant and that works. And that is the same spec for not only for the nodes, but it is for the total bus length of 25 meters. Meaning if you have you can have a maximum length longer than that. But if your bus only can go 20 meters, you're not compliant. And then the distance between any 2 nodes, and this is a bad picture here, but the distance between any 2 of these sensors, it has to support at least up to 15, it has to support 15 meters as the maximum between 2 sensors. All right. If you only work up to 10 meters between two sensors, you're not compliant. So it's these minimum maximum kind of specs. Just to kind of show you, if you look at this, so this is 8 nodes, 25 meters total length across all the nodes from end to end with 15 meters between them. We have a demo that we showed at actually at our masters last summer, that was 100 nodes on 100 meters of cable. And it just worked fine. Maximum length was 100 meters. They were a meter apart, and we did 100 nodes off of this thing here. So again, that's compliant. You just have to make sure that your maximum is at least what these numbers are as far as supplying. What it looks like when you roll this out here, obviously it's a single drop bus. You can have multiple things connecting off of it. With legacy Ethernet, it's just kind of a star pattern. So. And that's kind of traditional. Back in the old days, there used to be this kind of a shared bus kind of application with Ethernet, this 10 base 2, which isn't used anymore, or the concept of hubs where they had multiple things on it. That used this collision mechanism called the CSMA CD, which was carrier sense multiple access collision detection, and really all that does is you listen, and if nobody else is talking, you go ahead and talk, and then you kind of watch and make sure nobody else also started talking at the same time you did. And if you did, you both back off, and different nodes have different back off times, and then you try again after your back off time. It's not efficient. It's not deterministic. That there could be a case that you get into where your collision just keeps on happening over and over again, and you never get a chance to send. Obviously the probability goes down, but the point is that it's non-deterministic. So with T1S, they invented this thing called physical layer collision avoidance. There's a little animation here I'll go through on this too here. But essentially what it is everybody just gets a chance to send their node, their packet, their frame when they want to send their frame. With this coordination they do, now you've got some, if you have ever heard about token ring, where you basically everybody gets a time slot and you can send your data during that time slot. This is a little bit different because if you don't use your time slot, it gets short circuited and you move on to the next person right away. And so what that gives you is the efficiency of, if it's your turn to transmit, you can go ahead and do that, and you're not going to get collisions, and it's always going to work. But if you don't have anything to say, you're not going to use up that time, because we're going to short circuit and everybody's going to move on to the next node and give them a chance. So a very sparsely, one node out of 8 wants to transmit. It's a bunch of short circuits, and then one frame gets transmitted. Now, if everybody wants to transmit, then it's everybody gets a turn and a chance. So this PLCA thing is really kind of key to how the T1S works. But I should note that you don't have to use it if you don't want. You can always drop back into this collision sense where you basically talk and hope you didn't run into somebody else trying to talk. But there's some cases when you might want to do this, like a network discovery or something like that. But in general, the physical layer collision avoidance really helps you maximize the bandwidth of the space and makes it deterministic. You may not know how busy it is, but at least you know, here's my worst case chance to transmit, assuming everybody is trying to transmit. And here's my best case chance to transmit, assuming nobody is trying to transmit. And you now know it's a bounded problem. You know your worst case latency or your best case latency, and it's deterministic. And that's kind of important in a lot of different applications. So some more detail, and I kind of jumped the gun a little bit on this one, but what I want to point out is when each of these has a turn to transmit, and you get the short circuited, there are ways that you can make it unfair. So let's say you took a node that has really got a lot of important information. You always want it to have the lowest kind of latency. You can assign multiple node numbers to that node. So, for example, what I have here, if I've got node 1, if I want node 1 to have a lot of chances, I'm going to give node 1 node number 1. I'm also going to give it node number 3 and node number 5 and node number 7. And now it will always have a chance, with the worst case of one other person having a chance being in the middle of a transmit when it's time to go, if that makes any sense. And this is kind of what it looks like. You get a beacon gets sent out, node 1 gets a chance to send. If node 1 doesn't have anything to say, then you just kind of short circuit it. And then we go on to node 2's chance to talk. Once you've gone around through all the nodes on your that are on the bus, another beacon gets sent. And so, like, here's an example of if you send a beacon and nobody has anything to say. So you go through it, 0 through 5. They all try it. They all don't say anything. What's nice about that, if let's say you have a network that you have designed for 8 nodes. If you only have 3 things to put in at the start and you have got like 5 slots for growth, you don't have to change anything, because I don't have anything to transmit is simply to be quiet. And so if nothing is there, you just automatically be quiet. And the overhead that you're talking about, that is really minimal. It's like 16-bit times or 32-bit times of nothing says, oh, okay, it's time to everybody move on to the next thing. And so what you'll see, like in an automotive application, maybe there's some features you got a base model. Maybe there's some features that your car doesn't have. Like I don't know, like a car wash, a motor to pump your window wash onto your headlights, for example. You can still set up that bus in order to have that motor on the bus for all the models, and then only the top models get to actually have that motor installed. But the software to support all that is exactly the same, if that makes any sense. And then there's some more detail about how this works. Here's that example I was showing you where you take a node. I was talking about this earlier, where you take a node and you give it multiple node numbers. So in this application, that yellow node there, it gets as much bandwidth as everyone else on the bus, because he gets to talk at node time 1, 3, and 5. And the fact that he's spaced like this, there's never going to be more than one busy node happening between his chances to talk. If that makes any sense. So that's how PLCA works. It's a pretty straightforward, pretty cooperative kind of instantiation. There are some details. There are some that I'm just kind of skipping over lightly. There's such a thing as a burst mode. Certain nodes can be tagged that they're allowed to send more than one node. And there's a way of terminating, more than one frame. There's a way of terminating the frame transmission that says, hey, I've got another one coming. That everybody on the bus can see, so if there's multiple frames from somebody. So those are some kind of applications. And then there's some mechanisms for how do you discover how many nodes you've got and get nodes assigned. Now, in general, today, these are almost all designed networks, and at manufacturing time what the node numbers are and who's on that bus. The standards organizations are currently, as we speak, working on some discovery protocols where you can throw a bunch of non-node numbered devices onto a single network, and they will figure it out and get nodes assigned. And that's one of those reasons why you might want to use a CSM CD application time for those ad hoc, when you just have a bunch of stuff out there. And so you're going to basically do this inefficient kind of jabbering kind of thing until everybody gets a node assignment. And then once you get that, you enable the PLCA to coordinate it. And then all of a sudden now your bandwidth goes way up. You have much fewer, you have no collisions now. And it's all kind of organized and working to the kind of efficiently. So anyway, PLCA, it gives you opportunity to do a lot of things. And it's one of the keys of that is that it's deterministic. You can know worst case and best case times to get to receive or to send frames. And once you know what those worst and best times are, then you can do all your calculations in your networks and you can figure out, what your cycle time can be and all of those kinds of things. With a collision sense multiple access CD or kind of an ad hoc kind of thing, you can get into these situations where statistically they may be not super likely, but you get these things where a particular node can be really long time to try to send it just because of the way the timing and the way the interrupting happens on that. So that's one of the advantages of PLC is that it's the determinism. Um, so at that point, this is a 2-hour class that I've kind of squeezed down into 20 minutes. I'm going to talk about a little bit of where this is going from a product standpoint. And if you're familiar with Ethernet at all, this should look kind of familiar, is that you have in an instantiation where you're using an Ethernet product, this MII, RMII, or at the gigabit speed, RGMII, is a standard interface that you have off of switches and microcontrollers in the world. And so the first products out with this is basically just a different PHY. RMII, MII kinds of interface, and it has a T1S line PHY out here. And again, what I'll point out is that this microcontroller here doesn't have any idea whether this is a T1S multi-drop bus or if this is a 100 megabit, standard Cat5e driving Ethernet cable, or maybe it's a 100 base FX fiber, plastic fiber kind of thing. This MCU software doesn't change when you do that. And what's interesting about that is that you can actually have instantiations where you put down a T1S PHY in some designs, and sometimes you put a 100 base TX PHY down in here, and you didn't have to change any software on it. It just works. So anyway, so the middle piece here, this is really showing you what they call as an Ethernet controller. When you have a microcontroller with an MII or MII interface in it, the MAC, the media access layer, the layer 2 of your Ethernet stack, is built into the microcontroller. If you've got a microcontroller that doesn't know Ethernet, but happens to have a SPI port, then you can use an Ethernet controller like this. And essentially that MAC thing is being built right into what the PHY is. This is a little more expensive part, and it's a little bigger part because it's got some of the stuff that you normally is in the switch or the MCU is built into the PHY, but it allows you to use your favorite microcontroller even if they don't have any idea what Ethernet is. So it's just a SPI connection. And so these are all products. These are existing products that we are shipping today. Other suppliers are shipping them. This is the state of it. Where this is going next is really going to be key to cost reductions in this system, and from area reductions on how this is to implement. And as I talk about this, these are products, and this is a new thing that's coming here. But there's an organization in Ethernet called the Open Alliance for Ethernet, and they have defined a 3-pin interface that splits the PHY into its digital and analog pieces. And what this does here is that if you work with this OA3P interface, it allows you to put an analog only transceiver out here that really looks a lot like a CAN transceiver or a RS485 transceiver. That it's just an analog device that is changing the levels coming out of this whatever your host is. And so this is really inexpensive and it's really small. And they do that by kind of splitting the PHY in half and taking what's digital and moving it into something that is already digital. And that saves a huge amount of money. This over here, this picture here where the digital and analog are in the same die, it's either a digital die that's trying to do analog or it's an analog die that's trying to do digital. But in either case, something on there is really not on an optimized process. So what you do is you take this digital stuff and put it with the other digital stuff with it. And this could be a switch or a microcontroller. But how this was explained to me, if you have a Cortex M4 microcontroller that is built on a 40 nanometer process. It's really small on a 40 nanometer process. Well, if you want to put that into a 32 pin package, because that's the I/O that you need, the bonding pads on that die to support the 32 pins leaves a space in the middle where you could probably fit 2 or 3 Cortex M4s in there, right? Because it's the I/O ring, the I/O pad that defines the minimum size of that die, because that's the I/O that you've got. And I mean, unless you want to go to a fancy ball grid array kind of package. I'm just talking about a leaded package or a PLCC kind of thing, that has those many connections on it, and it's got a wireframe. It drives the die size. And in that case, adding more digital logic to that processor is really almost free, right? You're not making the die any bigger by putting more logic in it. And that's a lot of reason, you see the microcontrollers these days are having larger and larger peripheral sets. And not just more peripherals, but also, smart mechanisms for having peripherals talk to each other while the microcontroller is sleeping, and those kinds of things. Because the I/O is what's driving the die size, and hence the cost of that part, really more than the amount of logic that's in there. So again, this kind of a move is almost free on this side and really makes this a lot cheaper. And so what this is this move here that we're doing, is going to drive costs down even more. And I would see by the end of this, we already have this transceiver part. We already have that part done. But our first microcontroller that will have an OA3P interface is due out later this year. And that will be kind of our first step into this new world of really doing T1S at kind of the next step down in costs. But anyway, that's where that's going. And what you're going to see with that kind of implementation is that you'll start seeing switches that look something like this. So this is kind of a next generation switch, and this is just this isn't a specific one that I'm talking about here, but this is a switch here. And what I want to draw your attention to is this area down here in green in the lower middle here. This is a 36 pins that you can use for RMII or RGMII or MII, or you can put up into 36 pins, you can put 8 of these OA3P interfaces. And remember, this OA3P interface, it's a 10 megabit interface that is a multi-drop bus, meaning that you can have 8 buses, each that have 8 or more nodes on them, all coming into a single switch with this one, with just a minimal of pin interfaces to do that kind of thing. And so like I said, this is kind of a much higher performance switch than you would typically see in a system that's using a bunch of T1S. But with kind of the security requirements that are coming, a lot of the redundancy aspects that you want to do, there's a lot of smarts that are kind of coming into these switches these days. But they just show you how efficiently you can do a huge amount of nodes all coming into a certain thing with a low amount of pin count. So with that, it's been about a half hour. So at this point, I guess I would like to leave it up for some questions.